Thank you, Susan, for inviting me, and thank you for attending this evening. So my topic is, with basically a perspective of how do we design software. Is it top-down design or bottom-up design? So this is where the floor-to-ceiling or ceiling-to-floor expression comes from. What do you think it should be? Do you have a preconceived idea of where you think how software should be driven in design? And when I talk about design, I'm actually talking about implementation as we design. So it's not big upfront design or a lot of big upfront analysis. So hopefully I'll be able to help you with this perspective today. So I'm working on this open source project called Vlingo. Some people say Vlingo. I say Vlingo. It doesn't matter to me as long as you use it. So I welcome you to try it out. Currently, we're at version 0.8.2, ready to release 0.8.3 soon in Java, and the .NET edition is lagging a bit, but that's because it's based on the Java edition. And I'll talk a little bit more about that as we go along. So, domain-driven design. If you are somewhat familiar with it, you've probably realized by now that domain-driven design is pretty much about this: the bounded context and the ubiquitous language. And of course, there are several other tools that you can use with domain-driven design. There are strategic modeling tools and tactical modeling tools, but I just want to set the perspective that when I'm discussing DDD, this is pretty much what I'm thinking about: the bounded context with a ubiquitous language. And the bounded context sets a boundary for where certain terms and expressions have applicability, where they have a specific meaning. And so inside a bounded context, the ubiquitous language is an understanding of team members and how they develop the software as a model, okay? And then from the reactive perspective, notice that I've decided not to represent the objects in this diagram as rectangles or squares like a lot of people do, but I've purposely chosen circles. And that's sort of a historical decision or direction that I got back in somewhere, I think it was the late 1970s or somewhere in there. Someone named Gul Agha has wrote a book about the actor model, and Dr. Agha decided to represent actors as circles. So I have, and actually some books, other books about the actor model have also represented actors as circles. Now, I just want to explain, when you think of actors and the actor model, you may be thinking, oh no, something I'm going to have to go read for hours about, something I don't understand. If you don't know about the actor model, just think of it in this way. Actors are objects, okay? And actors receive messages. So if you ever use Smalltalk, the language Smalltalk, Smalltalk was based on message passing. Objects received messages. And so when you wanted to ask an actor, or I should say an object, to do something, you asked it to do something by sending it a message. This could be a command message or a query message or whatever kind of message you were sending, it was a message send. And this is basically what the inventor of object-oriented, Alan Kay, had in mind when he came up with the object idea. So he says that message passing is the big idea in OO. So think of these little circles in this diagram as objects done right. And so the lines between them are not necessarily dependencies, although you could think of it in that way, but it's actually representing messages being sent between these objects. And it so happens that although Smalltalk was originally written as a blocking message send environment or language, more modern renditions of the actor model are using asynchronous message sending, okay? So think of, when you think of the actors here, think of objects that when they ask for some service from another actor, they are not blocking, okay? Instead, the message is sent asynchronously, and wow, that just, what happens next? What happens to my object when I send a message? How am I going to find out the result? That's actually sort of the hurdle that you have to jump, stride over if you're going to understand how to use actors in our contemporary times. So I'll get into that a little bit. But now the question is, should our systems be developed top-down or bottom-up? Do you already have a strong opinion on that? Frankly, I've heard some very strong opinions on this, and some of the strong opinions, kind of are expressed like danger. If you don't take the top-down perspective, you're just gonna, mess up the whole system, right? That you're working on, because of course you must have this, sort of grand scheme idea of how things are going to work from the beginning. And I would say that that's probably actually the real danger, is trying to know everything up front. I think that that's really waterfall thinking. And so I'm going to try to contrast those two, ideas of are we really in danger by taking a top-down or taking a bottom-up perspective rather than a top-down perspective. Now, I just want you to consider this little image that I have here, and think about what you envision this as representing. I mean, I think most of us would say, oh, that's, some galaxy, right? And okay, let's take it as a galaxy for a moment. Where is up and down in the galaxy? Right? I mean, when we're watching some sci-fi movie or TV series, Star Trek or something like that, we've always got this perspective of, the crew is right side up, aren't they? I mean, they're walking in gravity, and they've got this great opportunity to be just like they're on Earth, right? But what is up and what is down in space? Now, if you switch a perspective here and you say this is not representative of a galaxy, the stars in a galaxy, but what if this were the nodes on the internet, right? What if this were zooming, in quite a ways from the internet? What if this were the objects on one node in a cluster? So taking this perspective by, sort of zooming out, zooming in, what do we know about this? Can you jump in at any level and fully understand what's going on here? Or do you need actually multiple perspectives to understand if this were a software system or just one node in a software system? Or if it's a galaxy, and which is up and which is down. So I think I've learned a bit about DDD, and something that I think has been reinforced to me through others in the DDD community is that domain-driven design is about learning. So when you are using domain-driven design, probably, well, I'm going to just suggest, instead of being overly opinionated about it, I'm going to suggest that maybe if you're taking the perspective of entities and value objects and aggregates and things like that, maybe that's not really the strong takeaway that you should have with domain-driven design. DDD is about learning. And the big danger with using domain-driven design, if you do not approach it from I need to learn, is that you walk into a software project, maybe a large program of a whole system, and you take this perspective that you already know everything. And I see it actually all the time. I have to say, I feel bad about it, but I see this perspective where very experienced architects, software developers of all stages try to walk in and solve the problems on their own. And one of the biggest complaints around domain-driven design is, where do I find my domain expert? Identify who is the domain expert, who's the right domain expert that we have here. And of course, this can be a challenge to identify the domain expert, but frankly, when we identify anyone with domain expertise, are we actually engaging with them? Are we learning from them? Are we learning together? Or do we walk in as, sort of the hotshot software developer saying, I know everything already, let me show you the way, right? Then DDD is not a learning tool. DDD is just a set of tactical approaches to render some objects of some kind, let's say, or some functions with some records into what's going to end up being probably a real mess. So think of DDD as a learning tool. So I think the real danger is, sort of taking the perspective that you must develop software in a top-down approach, or even you must develop software in a bottom-up approach. The danger is that if we don't enter a project understanding that we have to learn in the project, we're missing really the big picture and even the small picture. So learning begets knowledge, and knowledge changes everything. I think this is an extremely important fact to embrace as we are developing software. So, reactive DDD then, do we insist on taking a specific perspective, floor to ceiling or ceiling to floor? Does it really matter? So I think that both top and bottom perspectives are strategies for learning and for ordering knowledge, right? So how do we even discuss what we know? How do we discuss what we don't know? How do we learn about what we don't know? And when we are considering this, just think of these two approaches as a style of thinking. You needn't reject either one of them because they're both quite useful. So let's learn about top-down for a moment. I think that top-down is mostly about what you already know. This is where you will discuss with people a larger picture perspective, and as you're doing this, you are sort of stepwise refining from the top toward the bottom. So you're decomposing problems. And problems at any given level look like black boxes. You don't really know exactly what's inside of them. And at some point, your knowledge of where you are from the top perspective will run dry. You simply will not be able to carry that level of knowledge all the way to the bottom. And so at some point, you will have to switch your perspective to a bottom-up perspective, and this is trying to discover what you don't know. So you're really piecing together a system. You are really taking the subs or the software that you're writing at the lower level from the bottom-up perspective, piece by piece, but then those actually become subsystems in the larger system. So we're taking an emergent approach here. There's a tunnel in Colorado in the United States known as the Eisenhower Tunnel. And I think I mentioned this in my red book, The Eisenhower Tunnel. And it was interesting how the crews that were working on drilling this tunnel through a large mountain in Colorado worked. And they decided to work from both ends of the mountain. So one crew started drilling in from one side, from the east side, and another from the west side, and they were supposed to meet in the middle. This was an interesting problem, and if you drive that tunnel today, you know what happens is there's a big curve in the middle because they missed each other, and they simply had to course correct, and then they finally found each other in the middle of this job. So, but you know what's great is there's a tunnel, right? So we're going to miss sometimes some important pieces of data in our decision making, but we can always course correct, and curves aren't all that bad. All right, so taking both perspectives then is a matter of showing that your knowledge is becoming pervasive throughout the system, and reactive DDD therefore becomes pervasive through the system. So if you take sort of that top level, I would say that the top level perspective is using strategic design. This is a ceiling to floor sort of perspective. Now notice, I'm going to switch slides in just a moment, and you're going to see the same information, but we visualize it differently. Information exchange is extremely important between subsystems in a whole system solution. To exchange information, we're often trying to look at this information from the perspective of the subsystem that is producing it. So this would be a bounded context in DDD. And so a bounded context should, if possible, create what's called a published language. This is not always possible, but I'm just sort of constraining this problem domain right now for the sake of this conversation or this presentation. So if we have information exchange, we're trying to create the best experience possible for exchanging that information between contexts or subsystems, and so we create what's called a published language in domain-driven design, if possible. And then you'll find that this published language is ultimately based on a model that is spoken on the team who's working in this bounded context or this subsystem, and this mental model that is spoken is rendered as, or what we would call, a ubiquitous language. So it's ubiquitous on the team. It becomes very important to the team because this is how they communicate with each other when they talk about anything but Friday night at the pub. Okay, so this language is extremely important. Now, if we take this strategic approach and we think about top-down, we're probably going to be looking at context mapping. This is a strategic design tool of domain-driven design that helps us to understand what is. Okay? Now, I just want to warn you about taking this perspective too far. Because when you do context mapping, again, you should be trying to understand what is and how your core domain is going to fit in with what exists. If you try to take this perspective to what it will be too soon, you may be losing out on learning opportunities. So it could be that this context map is one that exists after, in essence, the system is designed or understood much better than when you start. It could be that only a few of these ellipses, or what are representing, various parts of the system, exist right now, and some of those may actually not even be green. They may be brown, like a big ball of mud. Okay, so this is one perspective, the top-down perspective. If you are thinking in the tactical perspective or thinking floor to ceiling, then you are using the tactical design tools. You are thinking in terms of your model. Now notice, did you see, these are the same 4 points, but they're in essence upside down now, because the mental model is developed within the team before anything else exists. You have to have conversations about what you don't know. And so as you are learning about what you don't know, you are forming a ubiquitous language. But the ubiquitous language will change, it will be refined as time advances and as you learn more as a team. And that ubiquitous language can then be have an influence on what you decide to publish to the outside world, known as a published language, about your domain model, your bounded context. And then finally, because we have a published language, we can now exchange information comfortably, reliably between subsystems in this whole system solution. So do you see how now the two perspectives are actually quite important? Okay, so if you think about a bounded context with ubiquitous language, this is probably mostly a bottom-up approach. And it would be a mistake to lose the opportunity to learn about what is actually core in your whole system solution. Because if you do not understand core, you're likely going to put effort into the wrong places. Okay? Now, if you need to take a top-down perspective at some point, you can simply define an interface that you want to integrate with at a lower level. This can set the stage for how are we going to, communicate with what we don't understand yet. It's a placeholder, if you will. Eventually, that placeholder will be refined and you'll take the perspective of, now I actually have something that provides the implementation to that interface, and that will be on the bounded context. So you can take the top-down perspective, but eventually you're going to have to build the bounded context that you're integrating with, and as you do that, you will now shift, or the team that's working on that will shift to a bottom-up perspective, because they have to have deep learning about the domain model that they're in. So now, when you think about the context map that I showed earlier, what did it have? 6 or 7 different contexts displayed in it. That was a top-down perspective, but now notice we have 3 contexts here that are being refined, and as they're refined, now we are taking a bottom-up perspective, but those will become the subsystems of the larger system. And so in essence, we can actually build the tunnel from both ends, and of course we'll have some course corrections as we go, all right? So what is this? This is sort of what we've achieved now, right? So is this a bottom-up perspective or a top-down perspective? How did we reach this point? Hopefully both ways, from both directions, because if we didn't, we probably did not learn enough about where we're working. Okay, so now we have to exchange data between subsystems. These are 2 bounded contexts with actors running within them, and the sort of blue and orange and white things between the 2 contexts are the packets of information that are being exchanged. And we can simply think of those as a certain kind of message, okay? So I've written a book on reactive programming, and I represent the messages between objects or between systems as using this kind of notation, which I think is relatively familiar these days. So the blue represents a command. So a command is being sent from the bottom context to the top context. And the orange is an event, and the event is being delivered from or sent from the top context down to the context that's underneath it. And it could be that we've also used a query from the bottom context to the top context, and the white message represents a document. It's simply a document message that's being returned. So these are sort of like the three kind of primary messages that are exchanged between systems, and we give these well thought out names. This actually, the things that are traveling between these two systems could be the published language. Who owns the published language from this perspective? So it would actually be the top system, most likely. So the top system has a published language that says, if you want to make a request of me using a command, you must follow this schema for giving me that command. And if you want to consume events from me, I will produce events that look like this, that are orange. And if you want to ask me for information through a query, you can expect that information to be delivered to you according to this particular schema, okay, in the white message, the document message. So if you kind of take that perspective, or you know, that kind of constraint of the messages that are exchanged between systems. Not that you have to be limited only to those, but it helps you to reason about at least the kind of language that you want to make accessible to other contexts, okay? So, what is a published language? It is really a schema, okay? At least from my perspective, you know, I think of a published language as a schema, and we have a schema that defines the commands that we accept, the events that we publish about some happenings within our model, within our bounded context, and we also have a schema that, or schemas that define the document information that we exchange between contexts. And if we're really doing this carefully, we probably want to have something like a schema registry where our own published language is not only understood to our team, but very well understood by any who decide to consume this published language. Okay? And then, if we're taking the bottom-up perspective, we are talking about our published language being available to consumers outside of our own bounded context. But if we take a top-down perspective here, what's happening? We are basically the top level looking at what can we consume from this bounded context. So you need both perspectives. So really, reactive DDD, as in I send a message, I receive a message, right? In any of these scenarios, that's what's happening here. Reactive is actually pervasive through and through. And also, wow, I got to tell you a story just briefly. But boy, I used the E word here with an architect one time. Oh, I got in so much trouble. Emerging architecture, you must be joking, right? No, actually, if you know what you're doing these days, architecture emerges. And there are good architectural styles and patterns that help you to succeed with an emerging architecture. But if you try to even attempt to make your architecture immovable from the beginning of your project, I believe that you're gonna, well, it just won't succeed. Either you will adjust your architecture or you'll fail. I don't have any opinions, by the way. And emerging architecture is lean architecture. It's agile architecture. It is agile design. So keep that in mind. So when I'm talking about an architecture that is lean and agile, and emergent, this is the kind of pattern that I'm talking about. This is known as the ports and adapters architecture, or you may have heard of it as hexagonal or hexagonal, however you like to pronounce it. But this is where the heart of the system is, or the heart of this subsystem, this bounded context, is the domain model inside, and then around that is an application layer, which may or may not exist depending on the tooling and the approach that you're using. And around that is this infrastructure layer. And the infrastructure provides input and output to this bounded context, in essence. And so what we're doing is we are adapting, so ports and adapters, we are adapting data from the outside to the inside, so what the inside can use. And when we produce data on the inside, we are adapting that data to the outside world. So this is ports and adapters. And now, because each of these layers and each adapter in the outer layer, or each style, or I should say category, let's say, of adapter, can be created and tested in isolation, this is a very, very agile architecture. It is a way to make emerging architecture work because you only have to understand the adapters that you need when you actually need them. You don't have to decide up front, will we use a relational database? Will we use a document database? Will we use an in-memory grid? Will we use messaging? Will we support REST? All of these decisions can be made when you learn more about it. But you can still start at any one of these layers, and you know, if you're starting at the infrastructure, this may be, at least to your team, a top-down approach. If you're starting with the domain model, it may be a bottom-up approach. But I'm going to suggest that in this situation, you really need to learn about the business model, the domain model, because this is what is actually going to be the thing that drives your single architecture. And then, if we have, you know, a number of these ports and adapters based bounded contexts, then they are all very lean, agile, and capable of emerging. In fact, even the information that we exchange between the bounded contexts will emerge constantly. And this is also a very important reason why you need something like a schema registry. Okay? So this is a design boundary. This is where a ubiquitous language is designed. This is where you will have REST endpoints, if you will, resource handlers. This is where you will have your entities. This is where you will have documents that are rendering the result of a query that is executed for you. And then when you look across the system, isn't it interesting that from the user perspective, well, they're simply using the parts of the system that they need, the different subsystems, and this may be in a single view, this could be in separate views, and this is, I think, a very logical way and to produce software. Okay, so we're now back to a danger zone. So I talked about the danger of being too opinionated about top-down or bottom-up perspective because you could miss learning opportunities, and other reasons for, you know, potential danger. But I think there's another danger that we face as software developers. And sometimes our core domain kind of looks like this, right? As software developers, we kind of have the fear of missing out. And what do I mean by that? Well, the fear of missing out 1.0 is, you know, what mechanisms are we going to use to succeed? And fear of missing out 1.1 kind of looks like this, right? So you change your perspective, and of course you can solve every problem with Kubernetes and Kafka. And notice that your actual core domain is now downstream from the actual problem-solving software which is actually infrastructure. And the fear of missing out is addressed, but what about the business? I think this is where projects get high-centered. Now, if you want a lot of people to read your blog posts, tell them that you're doing DDD like this, right? That's how you get blog posts read. And I think that, Kafka and Kubernetes, or Kubernetes and Kafka, they just go together. It's like crackers and cheese, right? So don't miss your opportunity there. Okay, well, this is the real danger. So when you're using DDD, you are using a distributed architecture. It's distributed computing. And the danger is that you will see disconnections. So I'm looking here at a medical domain. This is where we have a machine that is that is a host for a treatment of a patient, and this might be a dialysis machine, right, where a patient is not, they're not able to expel waste from their system, and so we have to help their kidneys a bit, and we put them on a dialysis machine to clean their blood. And this is a very, sort of fulfilling and rewarding business model to work in because you're actually helping people. So, when you think about this machine that may be in some remote location in any country, because people everywhere have diabetes and renal failure, it could well be that the internet connection between the remote facility, this clinic where the machine resides, where the patient is being treated, and the actual location where the data is being collected and where our main core domain resides on servers, you can have what's known basically as a disconnected operation pattern at play. So how do you deal with this? Well, one of a very important perspective to take on this is that every reading that you get from a dialysis machine on a patient should be collected as a series of facts, and these facts can be treated as domain events, because if there is a disconnection, you still have the history of everything that has happened with the patient on the machine side. And when this disconnection occurs, you can simply use normal patterns, as we know, maybe circuit breaker and with exponential backoff, to prevent flooding the network with requests that are just going to fail. And so once we are connected again, we can resume delivery of domain events to the main system. Now, these domain events are, as I said, facts. So this is a very important means of communication. Another thing that we can experience with, and is very likely to experience with distributed computing solutions, is duplicate message delivery. So what happens, and if you see it, I guess would be the far left of this diagram, you see duplicate domain events arriving, and as we see each of those domain events at our boundary, we're actually going to turn those into commands, because those are translated into an imperative that says internally we should do something because this happened elsewhere. Okay, so this is where the language, the published language of the other bounded context, is translated into our own language internally, and we say, do this because this happened. Okay, now what if those messages, those events, were delivered multiple times? It would naturally mean that the same commands are translated multiple times, and the stimulus on the entity is delivered to it multiple times, in essence, right? The command says, do this multiple times. How do you deal with that? Actually, you could go about using the deduplicator pattern by trying to save all events that have ever been seen by this system, or you could simply put the knowledge on the entity itself that says, I've already seen this, which is simply a status or some sort of a natural model element that you keep on the entity, and just let everything that happens from the outside travel in, and the entity at the smallest, at the sort of smallest granular point is deduplicating by itself. And we simply don't need this very complex infrastructural solution on the outside. This is showing a commutative sort of deduplication. A non-commutative deduplication is similar. It's just that this actually does need some sort of look-aside data that says, okay, I have absolutely seen this, whereas the commutative is non-damaging, repeating command. Let's say the non-commutative could, such as a financial transaction, if we have a withdrawal of money that happens multiple times, right? The same withdrawal, that's going to be very upsetting to the account holder. And you can well imagine, while that is only a financial situation, what if this sort of reading affects the way that a patient is viewed and treated later on? So this could be quite a bad consequence. So we have this look-aside data, and therefore, even though we receive multiple stimulus from the outside world, we only emit a single domain event in result of that. We also experience out of sequence. Again, let them all through in whatever sequence that they occur, and we simply take the decision that we don't care what sequence they arrive in. We simply will only take the next step when we know it is safe to do so, and that is when essentially event 2 and the corresponding command that is executed against the entity will be the one that corresponds, and we simply will not take the next step until we see all three of the stimulus that we were expecting. Okay. Blocking. When we're in reactive, we can run into the situation where we have a thread pool that is being used by actors, and if the actors are directly in our sort of service level thread pool, or what we might think of as our application thread pool, if those actors are being, if those threads are being consumed by actors that block, this is a big problem. So what we can do is block intelligently, smart blocking. It's not that we will never block, it's simply that we want the thread pool that runs the actors that will block, not taking away thread resources from the actors that should not block. This way, the threads on the service thread pool will be reused, and we allocate enough I/O threads in a pool to handle the throughput of our, for example, disk access. Another problem that you can have with the actor model is sharing. And it's not that, for example, you must never ever share. You should never share the inside of your actor as an immutable state. But, for example, what if a request arrives on your web server and your web server wants to take a shared, a byte buffer or something like that, some kind of buffer from a buffer pool, put a request into that and delegate the parsing and handling of that request to some other actors? What can happen is you can actually, what is very unusual is to see deadlock in an actor-based solution, but you will see deadlock if you do this. And so what you can design to prevent this is an elastic buffer pool where you are simply dynamically allocating more buffers as the demand goes up so that you can scale with that, and then shrink that elastic buffer pool as demand goes down to prevent deadlocking, for example. Okay, in the domain, a domain of healthcare, the DDD learning that you will experience is around the clinical data, the patient behavior, and their sentiment. So Does the patient follow doctor's orders? Do they take their medication? Do they show up for treatments that they should show up for? It will also include pharmaceutical data. What are the findings along the kind of medication that we are prescribing? And what does research data show about the kinds of diseases that people have, and how can we help to treat those diseases better? So this is the kind of learning that we have to use. And I think that in the medical industry, the digital twin sort of approach to software development is very useful. And so if we're in a clinic situation, a medical treatment situation, the clinical data can be collected through a digital twin. And the patient behavior, we can actually model the clinic data and the patient behavioral and sentiment data in digital twins. Now, I was doing this long before there was the cool name digital twin, but that's how we know them these days. So we simply create a digital twin for the kind of medical devices that we have here, and we can also create the digital twins for or digital twin for the kind of patient that we have. Are they taking care of themselves? This is showing a home dialysis, which is becoming more demanding these days because people who are on dialysis spend a lot of time going to clinics, and it takes up a lot of their time. And so if they can be at home while they're getting a treatment, this is quite a relief to them. So in domain-driven design, we're looking at how do we model the clinic treatments, and also how do we diagnose the patients within the results of those clinical treatments. So we are actually using big data, fast data, and analytics to diagnose what are the future treatments that we would want to have. So what do we do to get there? It certainly helps if we can design Fluent software. So the Fluent software can be both at the API level, so this is the actual tooling that you will use to create reactive models and how you control those models. So this is a concept that's similar to Future, but is much more coherent and understandable and really elegant than general Future interfaces. And so this is how you model the idea of we have an asynchronous outcome, and how do we deal with that asynchronous outcome when it actually happens. So it makes it very easy to reason about using this. We also want to model the machine. This is where the machine will be represented by a domain object. The vitals are represented by a domain object, and the treatment and the criteria and patient are value objects that can be held by those. And so we can tell the machine to gather patient vitals. Doesn't that read just crisply, very nicely? There's no, machine.set some small attribute of what a vital is or what a patient is. Instead, what we're doing is exchanging whole concepts, and by exchanging whole concepts, we're telling the model what we want it to do, just like objects were meant to be used. I think the thing that disappoints me so much about the really vast number of communications that are being made, or judgments against object-oriented programming, is that object-oriented programming has proven not to work, and yet probably 99% of all people claiming to use object-oriented don't actually use object-oriented programming. So I think the failure is really with their approach, not with object-oriented programming. Okay, so when we have a Fluent sort of class, or what becomes an object, this can be a vitals, which is actually a subscriber, but look, we don't have to call it a subscriber, it's just vitals. Internally, it's a subscriber. It's actually a stream, a stream-based, reactive stream-based subscriber. And yet, what do we know about it from the outside? Simply that it is a vitals, and we get a reading from a machine, and we tell a treatment to record the event of that action. And here's the use of the Fluent API to handle the reactive asynchronous. So basically, by the time the first and then to is actually used, the thread that was running this code originally is far gone. It's already being consumed by someone else, and another thread will be doing this work as we go along. So this is just an idea of how you can model fluently with real objects that have real behavior. And all of this can be seen in Vlingo, the DDD-friendly reactive tooling that I'm working on. And you'll find there under development this Vlingo schemata or the schema registry. The overall reactive platform architecture is based on actors that run in a world, and the world has one or more stages that the actors play within, right? They actually react to information within stages, and the actors are designed to be completely non-blocking, asynchronous, share nothing, and you can have one actor sending a command message to another actor, an aggregate, for example. But this is just an object. Whether it's an aggregate or not, that maybe is up for debate. But the point is that all of this is asynchronous, and there actually is a very strong transactional boundary around the one that is labeled aggregate. HTTP may as well work the exact same way. Why not? In fact, that request that you saw earlier just a few slides ago is an HTTP request handler that is operating completely asynchronously, completely non-blocking. It's dispatching messages based on requests to the inside of the model. And then there is, of course, how do we balance all this? How do we talk between nodes in a cluster? Well, we do that through Vlingo Lattice, and then also under development is this Vlingo Streams, which is based on both streaming storage and streaming messaging. So if you get a chance, just take a look at this open source reactive platform. You can find it at github.com/Vlingo. And the .NET is just add a -net after that, and you'll get to the .NET version. So I don't know, do we have time? Oh, I'm a little over? Oh, I'm sorry. Okay. So I guess I'm a little over, but I'll be here after. Oh, I did have some books to give away. Is that okay?
Sure.
Sorry.
No problem. So we are running out of time, but you came with some gifts.
Yeah, so how do I do this, Daniel? What should I... Oh, you want to? Well, I can't have them ask a question. So what I do?
Yes, you can.
Okay. I can fling the book into the audience, and if it doesn't knock you out, you can have it.
We make an exception, okay? So you can, if you would like to ask.
Ask me a question and choose a book, if you would like.
Who would like to ask a question?
Oh, I love Berlin. Ich bin ein Berliner. Yeah. Which book do you want? Okay. The red book? Okay.
And there's a second question.
Oh, Jan, you can't have this book. You're writing a competing book.
Okay. I have it. How does event storming fits in this top-down and bottom-up?
Oh, did you notice the colors of all the elements in the models that I showed are the colors of an event-stormed model? So the aggregates or the entities are pale yellow, the commands are light blue, the events are orange. I don't know actually if there's an official color for a document, but those are white anyway. So yeah, it fits in perfectly with event storming. Here. I thought so.
But okay, we have another interesting...
Go ahead.
I wanted to ask how does machine learning fits into this concept of top?
So the events that are, so let's go back here. Sorry. There we go. So the events that are that are leaving the clinical treatments model are flowing into the diagnosis model. And we can actually even tell the diagnosis model to do things if we need it to, but typically in this case it would kind of be a downstream listener to the domain events, and the domain events pack enough information, knowledge to react to them. So good question. Okay, Jan, you're going to have to gift these books.
But at first, thanks a lot, Vaughn, for your talk.
Okay.
So a warm round of applause for Vaughn.
Okay, thank you
Jan.
for attending.